well. Also, for those of you who are here in attendance at Boston Medical Center, there are certificates of attendance which are available at the information table in the back of the room after the lecture. So if you would like a certificate of attendance, you can head to the back and pick one up. Also, many of you probably have heard, but I am leaving Boston Medical Center and Boston to go to the University of Louisville. I was recruited there to be Chief of Spinal Cord Medicine and Director of Translational Research, and one of the things that was very exciting to me about the possibility of being there was the epidural stimulation research that Dr. Harkema is going to talk about tonight, and I will be able to participate with her on this research project as well as others. Leaving is very bittersweet. Many of you have become like dear friends and family to me, and I will miss you. It has been an amazing opportunity here in Boston for me personally to have my career grow, but more importantly than have my career grow, it was to make lifelong friends with many of you who are my patients and your families. And I want to tell you that you all mean the world to me, and I will miss you very much. I am excited to go to Louisville, and when I think you see the talk tonight, you will understand the excitement that pulled me away from Boston. So I hope that you'll know that I'm not far away, that we'll stay in touch, and maybe I will see some of you in Louisville as well participating in these research projects. As well, more recently, Boston Medical Center has decided to close the Department of Rehabilitation Medicine, which is very sad for me and for all of us here at BMC. Essentially, as you know, Boston Medical Center has suffered significant financial losses over the last 3 years. And this year, the hospital continues to have significant financial losses. In the last year and a half, they've closed over 150 med-surg beds. And in the last week or so, after a financial analysis, they decided to close the Rehabilitation Medicine Department as well. As you know, this department has been in existence since 1955. It is one of the oldest rehabilitation medicine departments in New England, as well as the country. It was the first civilian spinal cord injury program in the United States. As well, it's the oldest residency training program in New England. So it is very sad to see this program close, but I want you to know that there will still be a core group of people who will be in Boston, who will be helping to facilitate events like this lecture series. Whether this lecture series continues in person like this or webcast to Boston is still to be determined, because a large portion of the money that supported this lecture series, as well as the annual conference, was actually funded by my physician group called the Boston Rehabilitation Medicine Associates. It cost about $120,000 a year to fund this bi-monthly evening lecture series and the annual conference. And it was funded by the Reeve Foundation, the Paralyzed Veterans Association, and by the Nielsen Foundation, and we were very grateful for that funding. It came to about $30,000 a year. But as you can imagine, with the closure of the department and my physician group, there will not be that extra money to fund the balance. So I am working with Claudine and others to desperately try to figure out a way for this lecture series to continue. I think it's very important for the community here, for the country, and for the world, and I think that we have seen that as this webcast series has grown in popularity, and there are more and more participants each time we hold a series. So I will keep you in tune to what will happen with the lecture series through our email our listserv, excuse me. I also want you to know that we will be holding a lecture in May, but have nothing planned after that at this point. We will notify you if that changes. Also tonight, I would like to pay tribute to Bob Raymond. We'd like to have a moment to acknowledge Bob, who was a key member of our technical team. He passed away last week. Bob was instrumental in getting our webcasting program off the ground and in helping to set the standards for the technical aspects of our lecture and webcast. He volunteered many, many hours over the years to help us with all of our recording needs. His talent, warmth, and sense of humor will be deeply missed, and we're very grateful for all the contributions that he made gratis so that this program could continue. So I'd like to introduce Dr. Susie Harkema. Dr. Harkema holds the Owsley B. Frazier Rehabilitation Chair in Neurological Surgery and is the Rehabilitation Research Director of the Kentucky Spinal Cord Injury Research Center at the University of Louisville. She is also the Director of Research at Frazier Rehab Institute and Director of the Neuro Recovery Network that provides standardized activity-based therapy for individuals with spinal cord injury at 7 national rehabilitation centers in the United States. Her research focuses on neuroplasticity of spinal networks and recovery of function after spinal cord injury. Dr. Harkema has published numerous scholarly articles on her research and has received several honors and awards throughout her career. In 2007, the National Spinal Cord Injury Association nominated her into the SCI Hall of Fame for achievement in research and quality of life. And most recently, Dr. Harkema was a co-recipient of the Reeve Irvine Research Medal in 2009, awarded to individuals who have made critical contributions to promoting repair of the damaged spinal cord and recovery of function. In 2011, she received the Rick Hansen Foundation Difference Maker Award and Popular Mechanics Breakthrough Award. Dr. Harkema earned her Bachelor of Science and PhD from Michigan State University and conducted her postdoctoral fellowship in neurophysiology at the University of California in Los Angeles. So please welcome with me Dr. Susie Harkema.
Thank you, and really thank you for inviting me. It's such an honor to be here. Can you hear me? I don't need 2 mics, obviously. Is it working? Not well. All right, let me get a little closer. Is that better? Okay. Get it hooked on here. Okay. Let's get the slides up here. So as I said, I'm just really honored to be here. This is such a wonderful group of people. I think I've done this lecture series a few years ago as well, and it's one of my most favorite places to come and talk. And hello to everybody outside of Boston that's watching. This title means a lot to me because when I first started as a researcher at UCLA in spinal cord injury, there weren't really strategies for recovery, and especially not for people who had already suffered their injuries and are living with all of the devastating consequences of spinal cord injury. And it's so much fun to come and talk now because what I want to tell you is there are strategies coming out. It's not a silver bullet, they're not cures, but I think they have the potential to incrementally change people's lives who already have spinal cord injury. And so that's what I'm going to talk to you about today. Now, I have a lot of slides here, and I'm going to go really quickly through the first half. But I really want you to see the science that's behind this. And the key piece of information, I think, that is leading to these new strategies was actually the idea of it was initiated over a century ago. And it's taken this long for us to understand it in humans. And so I do want to spend a little bit of time just on the key ideas behind it. What I'm going to try to do as we go through these slides, I'm not going to, for those of you who are really interested in the nitty-gritty of the data, I'm not really going to talk about it, but I'd be happy to talk with you afterwards. What I really want to do is take this scientific information and tell you why it's important today for people who are on their lifelong journey of recovering from spinal cord injury. The original, and for this almost this whole century that I'm talking about, controls everything. But what's been known for over 50 years is that in all species, but presumed except for humans, there's a series of interneurons in the spinal cord that are called central pattern generation. And there's specific properties that have been known for decades about this. And what those properties are is that these interneurons, these nerves in the spinal cord, have the capacity to oscillate independent of input from the brain or from the periphery. So you just have a very specific preparation, and you can get what looks like walking out of just a spinal cord in a dish. Okay? The second, now, for humans to do those experiments, of course, you can't do those experiments with humans to see if the human has these same properties. But what my work has been for 18 years now has been looking at humans who have had what we call a clinically complete spinal cord injury. Okay, so one of the questions that I asked was, can the human spinal cord oscillate when we can't detect any influence from the brain? And so almost all the studies I talk about will be using that model. Another property of the spinal cord is that there's a certain inherent organization, flexors and extensors. So for standing, if your right extensor's on, your left extensor will be on too. What we know in every other species is that's controlled by the spinal cord. But we've thought that in humans, because we have this fantastic, phenomenal brain that we're in love with, that the brain does it. Okay? So, but in every other species, the spinal cord does it. Interlimb coordination, every other species. Okay? Now, these last two are what's so important for the potential for this to help people recover. Weeks, months, and even years after injury. That these interneurons are driven by information from the environment. Okay? Now, in an intact human being or an intact animal, of course, the brain has some influence, but the sensory information also has the influence. And the spinal cord becomes the decision maker, not the brain. It listens or might not listen to the brain. It listens to the environment. It takes all that information in, it integrates it, and it makes a decision about what that motor output is going to be. And if you do this over and over again after you've lost input from the brain, motor movement can improve with repetitive practice. So I'm going to go quickly through these slides, but I want to give you the background. The very first experiment we did in the early 90s was to take people who were ASIA A or clinically complete and step them on a treadmill, okay, and move their legs in a step-like pattern. And it was the very first experiment because if we saw no locomotor pattern, that would confirm this long-held belief that humans did not have these properties. But we were very lucky in that, ooh, what'd I do? Okay, that's not good. I'm not going to touch that. The first time we did this, we saw this pattern that looks like this. And for those of you who don't know, this looks like a walking pattern. It's not perfect, and they're not walking, and they're getting assistance. But this was the first evidence that told us that the human spinal cord might have the capacity to oscillate without supraspinal influence. Now, over 15 years, what we found is there's actually 4 types of patterns that we see the first time we put someone up on the treadmill. And I'm going to come back to this point later. But one, and luckily, this is not the pattern we saw the first time, because what would we have assumed? We would have assumed that the human spinal cord can't oscillate, that it doesn't have these properties. So we were very fortunate that that's not what we saw first. But we do see this, and I'm going to come back to that. Another pattern we see very often is that you have activity in one leg that so overpowers the other leg, and there's no interlimb coordination that's appropriate. The flexors and extensors don't behave well. And then here in this pattern, what is here is there is interlimb coordination. So my calf muscle on the left, when my calf muscle on the left is on, my right isn't, and vice versa. So we start seeing that. But if you look closer, all these muscles are on at the same time, and they shouldn't be during walking. When extensors of one leg is on, the flexors should be off. But we did see that. We have seen that pattern, even when there wasn't input from the brain. Okay, so that was some evidence. Now, the other evidence is what we did is we started doing very tedious experiments, and we said, let's change sensory information and see if things change. And I'm not going to go to the detail of the slide, but what this tells you at the top tells you the answer to the slide, that if we increase the load, so we have people in a harness and a body weight support, if we put more load on their legs, we got more EMG activity. And that's what you're going to see in all these slides. This is telling us this is our window into the spinal cord. This is measuring the nerves, and we're seeing from the nerves that, first of all, we can see a pattern that looks like locomotion, and secondly, we can modify that pattern with sensory information. Okay, so again, it's another property of central pattern generation, and this one is regardless of your severity of injury. If you don't have an injury, here's the non-disabled, you have an incomplete injury, or you have a functionally complete injury like an ASIA A. If we load you more, we get more EMG activity. So we said, you know what, here's another property, and it looks like it is independent of input from the brain, and it's something all people use when they walk. The next one is we changed the rate of information coming in. So we simply changed the speed of the treadmill. And so we went faster. And what you can see here pretty simply is when we went very slow, some muscles didn't have any activity you couldn't see any activity in the muscles. Simply by going faster, you saw more and more activity, and it was the right kind of activity. Flexors were relating to extensors like they should. Right and left was doing what it should. And this was kind of our second piece of evidence that this existed. Now, it was also thought that if there was some people who thought maybe the spinal cord does have a lot of control, but in your ankle muscle, the one that flexes your foot up, the tibialis anterior, when a person has a stroke, it seems like that muscle doesn't work well. And this has always been attributed to muscles in the brain. And quite frankly, at this time, we kind of thought that in the human that was probably the case. So Christine D., who is a graduate student in the lab, this was her PhD thesis, she asked that question, and she said, if I look at the calf muscles and the tibialis anterior, the one that flexes my foot, if I should see this alternation that you see here. This is the right way to behave. But if I see incomplete, sometimes I should see it. But if I have a functionally complete person, I should never see it. And it turns out that was absolutely wrong. That's not what happened. In fact, if you look down here in the corner, there were more people with an ASIA A injury that had that appropriate alternation. But you could see both patterns. Okay? You could see it in the incompletes and you could see it in the completes. So that told us, well, the spinal cord can do it. It doesn't always do it, but it has that ability to do those, have those alternate in the right way. Okay. Now, inner limb coordination. What do I mean by that? That the right leg and the left leg know what each other's doing, and the spinal cord's the one that really knows, but it controls it. Now, this is one of our very early experiments, and this is a young woman with an ASIA A. And what you see here, what you're going to see real carefully is that see how her leg moves there? Now look carefully. What I'm doing is I'm straightening and loading her leg, okay? And that sends a message to the other side for her to pick up her leg, flex it, and then extend her hip back to get ready for the stepping, okay? She is not thinking about doing this. That is coming from the information from the other leg. Okay, and this was a very important finding because it showed both things, that the spinal cord can understand what's happening in one leg, and it is information that decides what the other leg's going to do. Now, when we did this with people who had an incomplete injury and were able to, is that still going? Yeah, here we go. We were asking him to do that same movement right here, to flex his leg, and do you see he can't do it? But when we straighten and load the other leg, now he can do it a little bit. So that shows that that information from the other leg is important in him being able to do that. So this shows you again, when he flexes and unloads the leg, he can't do it. Now, when we trained him, remember when we were doing the training, stepping him, he started getting that movement back even when the right leg wasn't loaded. But watch what happens at the same time. If we just put load on the other leg, now his ability to do it is dramatically better. And so this told us that the spinal cord, the human spinal cord, can mediate inner limb coordination, and that the information from one leg can be interpreted to make a movement on the other leg, both in people with incomplete injuries and complete injuries. So now if you start looking at these properties, you see that we can slowly are starting to show evidence for these properties. Okay, now I'm sure that many of you know what this is when you see it, and this is clonus. Okay, many people out there, I'm sure, have experienced it. And I think here's clonus, you stretch the soleus and you get this clonic activity. And for many years, and I think many people still might think this, is that the idea is that because you've lost input from the brain, now your stretch reflexes are going crazy. And so when you stretch that ankle, you get this clonus. And that if we're going to help you recover, we got to shut that down. Okay, so people take medication to shut it down, they get injections to shut it down, and that then suddenly now recovery can happen because we shut down the bad activity maybe. Okay, well, Janelle Barris, another student in my lab, looked at this very carefully. And so this is what you see when you get clonus. When you and we call this clinical clonus, you see this very specific oscillating pattern when you stretch, and it's always the same. Now, if it was caused by stretching, okay, if you think about this side being your calf and this side being the TA muscle, then if you stretch this way and then stretch that way, okay, these muscles should be on what? Alternating. They shouldn't be on at the same time, right? Because they're stretching in opposite directions. They could never be on at the same time. And the first observation we saw was that they are on at the same time. And I had this figure up on my board for 3 years because I would go to my clinical colleagues and I would say, look, this can't be stretch reflex. And they would say, well, it is stretch reflex. There's something wrong with your data. Put it up there for 3 years, and then we decided to look at this really carefully, and it was very puzzling to us. And so what she did is she quantified muscle stretch, and the short part of the story is whenever you get clonus, whether you're standing or you're stepping, okay, because we all know you can get clonus in lots of different areas. This is the data here, what you see down here. All I want you to know about this is no matter what you're doing, if you get clonus, it's oscillating and it looks exactly the same. Now let's think about this for a minute. How else can you get clonus? If your bladder's full, right? If you're hot sometimes, if you're cold, if someone rips off a Band-Aid, somebody pinches you, right? You can get clonus. None of that is stretching a muscle, yet you can get clonus. So what's common about all these things? What is common? Stretching a muscle, heat, cold, bladder filling, sensory information, right? Sensory information. So it's actually any kind of sensory information is setting it off. And what is it setting off? A distinct oscillating pattern. And so what we did was we looked even further and we said, okay, look, we're going to stretch and get the left leg going, and then we're going to stretch and get the right leg going, and we're going to see what happens. And so we did that, and what we found when a person didn't have weight on their legs is that when and sometimes it came on together, sometimes it didn't. We did thousands of these, well, maybe hundreds of these, but we got thousands of bursts, and this just happens to be a time where it timed exactly the same. But look what happens by the second beat. It's alternating, right? Like you do when you're walking. The right and left soleus should be on alternating. And it stayed like that. So no matter where we were, by that second beat, it would alternate. If it was a little off, it was together. So then we said, well, let's look at what happens when we load. So the black line is when somebody's loaded. They have weight on their legs. They're standing up in the system. And here, look just in the center here. The soleuses, they're on together, right? They're on together. And when we take the weight off, here we took the body weight support up, so there was no weight on the legs, they started alternating again. And so when there's load, the soleus is on together, like they're supposed to be when they're standing. When there's not load, they alternate like when we're walking. And so this told us that we could access these oscillating patterns by changing the sensory information. And when we changed the speed of the treadmill, okay, here's somebody who has lots of clonus. You recognize that now. We went faster, and if it was stretch reflex, the faster you go, the more clonus you should have. But that's not what happened. When we put this information that's more closely related to what normal walking looks like, the clonus diminished. It went away. And when we loaded more, which is more like normal walking, the clonus would go away. So we could modulate this. And what would happen is that if we did it over and over again, before we would stretch the muscle and we get clonus for minutes, when we train people with locomotor training and we did that same thing, that same input, we didn't get very much clonus. So that told us that things could change with motor practice. And so what we concluded from, and those studies that I just went through in just a few minutes, 12 years of work right there. Okay, 12 years of work. So what we concluded at the end of that was in the human spinal cord, there are interneurons, like in all other species, that have a significant level of control of walking. Okay? And so why do we say that? Because we showed that the functionally isolated, and what that means is no input from the brain, human spinal cord can generate oscillatory patterns when we step and in clonus. And that's very critically, the sensory or afferent input that comes into the spinal cord can modulate those patterns when there's no input from the brain. And I didn't show you this data, but we also looked more deeply into the clonus issue and reflexes. We found that we could modulate reflexes in people without the brain. Remember I told you they thought without the brain the reflexes went crazy? No, we can modulate it with repetitive training and with sensory information. Okay, so this led to, at this point, when I was at UCLA when we did this work, and people would come in, and there were some people who were incomplete who went through this training. They came in their wheelchair, and they were able to walk. Not like normal, not before the injury, maybe only across the room, or maybe more, or maybe all day different, but then they had no access. The only place they could do this was in the lab, and so that was very frustrating. And this is why I moved to Louisville, Kentucky, and what we want to have at Frazier Rehab Institute is we're going to continue trying to solve problems, but when we incrementally solve one, we want to get it to people as quickly as we can. And that's our mission at Frazier. And that's what we have started to be able to do, both at Frazier and within the Neuro Recovery Network. Okay, so one of the other things that was really interesting about this was, remember those 4 patterns I showed you? Okay, the 4 patterns were for completes. And we said, well, okay, in incompletes, right, because they have more input from their brain, we should start as the best pattern, like and then the patterns should just get better and better and better because the brain's there. And so we did a big study, and we compared the patterns from people with incomplete injury who were stepping, and we were really actually quite surprised to find that they had the same 4 patterns. So if you look here, and I always forget which one's complete or incomplete, but at the top is incomplete and the bottom is complete. Remember, there was little or no activity? We can see that in some people who have detectable influence, can move their toes or ankles below the lesion. Here's that pattern, remember, that's stronger on one side and not the other. Here's, and so on and so forth. So if I covered this up, oh, that's not covering it up there, is it? If I covered it up here, I don't think you could pick out which was a person with an incomplete injury, Asia C or D, or an Asia A. So this, again, told us this spinal cord is really important. And if we can understand how it works, we can take advantage of it. And we probably really have never taken advantage of these properties yet. So people should be able to recover. So what I'm going to show you now is 3 levels of people with incomplete injury. They are out of inpatient rehab, out to over 20 years injury. And we call this a phase 1 of recovery. And I'll talk a little bit about that. But this is a person, as you can see, who cannot sit independently, cannot move her arms. She is what we would call in the earliest phases of recovery, right? She has a lot to recover. And certainly she can't stand or walk. So she entered our locomotor training program, which is standardized, is very intense, an hour and a half a day. And she was in this and it was based on those principles. So when we do locomotor training, what do? We train at fast speeds so we can get that advantage. What do? We load as much as we possibly can, and we progress that load as quickly as we can. And we step people with manual assistance. I'll show you here. Here's her early on. Oops, why is that? Let's get that going. You can see that the trainers and the therapists are really doing all that movement for her over and over again. If you look at the top level, right? She's not moving her arms, and she's very weak. But we did that over and over and over again at faster walking speeds, and what you can see after about 4 months is her on the bottom. And I think you can see that she increased her strength. She's got some independence. She's swinging her arms now. Now, she did not recover the ability to stand or walk. Here's what she recovered. The ability to sit independently. And it allowed her to go from a power wheelchair and complete dependence on her mother to a wheelchair she could manually push independently, and she went back to college. Now, at the time, she was 3 years post-injury. She had gone through all rehab that was thought going to be able to improve her recovery. And I think a lot of people, I think before the Neuro Recovery Network and the data that we have now published in the archives, would think that after 3 years, you're probably not going to recover very much. And it turns out we have new strategies now that can change recovery. Now, this is an individual. This is not a person with a stroke. This is a person with a spinal cord injury, but obviously much more affected. Now, he had gone through in and outpatient over a year post-injury, and of course, all of you know who deal with healthcare insurance companies, he was good to go, right? Fabulous. We have reached functional goal of walking. He entered the Neuro Recovery Network, and this is someone that we would call a phase 3 person. So there is a phase 2 who can just stand, but this is a higher phase of recovery because he's up and walking. So what we did is we retrained him also. And one of the things that I want to point out is that we also worked with his arm as well. Here, whoops. Okay, and we were, the team was able to stop assisting, and he was able to step independently with a normal pattern. So, and we had to train both of his legs, not just the leg that wasn't functioning well, but both legs, so we could retrain that original pattern. Okay, why is this not going forward? Okay, and this is what he looked like 4 months. After, well, probably a little more than that, probably 6 months of locomotor training, 5 days a week. He was able to walk without the assistance of his cane, and this was very important for him. It's not completely back before he recovered, but he had just had a new baby, and he couldn't walk and carry the child, and he felt like he wasn't helping his wife out because he had that limitation. So this change, even though he had reached that functional goal, what we call, I would say, a rehabilitation goal of walking, it still was incredibly limiting, and we could take that and we could incrementally improve that. Okay, so I want to introduce the 7 rehab centers: McGee Rehabilitation, Boston Medical, Frazier Rehab, Tier, Ohio State, Kessler, and Shepherd. Probably all very familiar names to you. At this stage, we have enrolled almost 500 people in the Neuro Recovery Network, and we have the data. I'm going to show you a little bit of that data, but pretty quickly, because I want to. But what the Neuro Recovery Network does, mission, is to take new evidence and translate it. And so our first was to look at people who had gone through rehabilitation already, who had ASIA C and D injuries, and see if we could improve their recovery. Now, just recently, and this is a busy slide, and I'm going to point you to a couple things, because I'm on 2 points about this slide. But the first is that I want to tell you we now have 5 community fitness and wellness centers. I'm not going to talk too much about them in the talk, but this is a place, they're standardized, activity-based interventions can be provided to people after they're discharged from rehabilitation in a fitness and wellness setting. And so I just want to quickly point out who those are here. Next Step is in Los Angeles, Courage Center, the NeuroWorks here, Next Step in Chicago, and there's also a community fitness and wellness center in Louisville, Kentucky at Frazier Rehab. And so this gives individuals, after they get out of rehab, ways to stay very active. And they do locomotor training in there, in the community fitness, but it's not focused on recovery per se. It's focused on health and wellness, because the other things that we found out about locomotor training is other things improve too. Cardiovascular function, respiratory function, circulation, muscle changes a little bit. And so in the rehab centers, we're using locomotor training, the standardized intervention, to improve recovery, and those other things are a bonus. And in this community fitness and wellness, sometimes people do recover function as well. And then they can go back into rehabilitation, but the focus is really about the health and wellness. And I certainly don't have to tell this audience how much that impacts people who have a spinal cord injury's daily life. It impacts them every day. All these other things, not walking, but bladder and bowel and all those other things. And I think that if we can understand or take advantage of these new mechanisms we know with the spinal cord, it may help those other aspects of spinal cord injury. Okay, so I introduced the NRN, but I want to just more formally tell you about the mission. The mission is to have standardized interventions across multi-sites that are activity-based therapy. What do I mean by that? Well, what I mean by that is targeting below the level of lesion. Okay? I think rehabilitation, and very importantly so, is very good about figuring out ways for people to use compensation strategies so they can get back into their home and community and reach rehabilitation goals. Very good at that. This is an additive to this, but it's focused on recovering below the level of lesion. And we need to have scientific and clinical evidence for that. So we started with locomotor training. As I already told you, we did C's and D's. And the key thing about it is providing sensory cues to retrain neural patterns. And I'm going to tell you, in all my years of studying, all reading animal literature, basic science literature, loading is a very important sensory cue. Our body needs it. And it turns out our body needs it not just for walking and standing, but for our heart to function right and our circulation to be working right. And so if I could give anyone any message, if you have the opportunity to stand or to get weight on your legs, I think you'll find incremental changes in your life. I think you will. Now, the challenge is at giving people access to that, right? Especially if you're a phase 1 early in your recovery. It's very difficult, but that's one of the things we're trying to do with the Neuro Recovery Network, is give people either in a rehabilitation setting or in a community fitness and wellness setting a chance to get up and weight bear every day, or you know, as often as they can during the week. Okay, so I'm not going to go to the details of the intervention, but I just want you to know that it's standardized and it's based on those scientific findings that I showed you. There's a part we call retraining, which is changing that nervous system. And once your nervous system changes, you have to adapt your task to that new function that you've been able to generate with that repetitive training. So when we take it into a clinical environment, these are two really critical things. And I think you hear a lot about body weight support treadmill training, or, you know, I think that's used a lot. And there's lots of different studies out there sort of debating how much does it work or don't work. But locomotor training, it's a very important phrase, I think, is the whole aspect of changing your nervous system and then adapting it so you can use it in your home and community. And it's an incremental process. It's very intensive. It takes a lot of work for people who are in the program. But what we have, I think, found now is that there is this potential for recovery even years after injury. And so I think there might be emerging new strategies for those of you who have been injured even decades. Okay, so I'm not going to go into detail here. Here's the colleagues who looked at this information on 199 patients. So when we looked at the data, so Berg Balance Scale, that tells you how well you balance. 10-meter walk test looks at how fast you walk, and the 6-minute walk test looks at how far you walk. And this is a very complicated slide, but here's what I want to tell you about it. We're plotting individual people here. And the biggest point I want to make here is even if you're an Asia A, if you're an Asia C, C or D, the scores are all over the place. They're all over the place. So people are at very different levels of recovery, and we need to understand that. And when you design an intervention, you have to figure out where they are in that recovery. But the other point about this is that going up means you're getting better. And it's true for whatever. This is speed, and this is balance. We went up. Now, one of the things I think is an assumption is that if you're an Asia D, that you have chance to recover. If you're Asia C, especially a few years out, you probably don't have much chance to recover. I think that's probably something you may have heard or you can hear, and there's a belief system. But what I want to do is you to focus on this and say, these are Asia Cs who are chronic, who've been out in the world, and they're improving with intense locomotor training. So one of the things that we're hoping is that when this gets published, that this will provide more access for people to come back and get their physical therapy paid for even years after injury. So, and that's one of the things that we're working on. Okay, so this is just for you to kind of visualize. These are all individual people. At the start, here's the start. We're plotting the start of their treatment and the end of their treatment. And what you see here, if they were not changing, they'd be on the line. If they got worse, they'd be underneath the line. But you see all these people above the line. 89% of the individuals improved on all three of these scores. Now, remember the first person I showed you? She didn't improve on any of those scores. She was what we would call a non-responder. Okay? But I think if we look at her video and how her life were changed, she did respond. We just weren't able to measure it with the outcomes that we have. So to me, this is really important that in rehabilitation, I think we have to think about, or it's really important to think about incremental changes and the value that that brings to people's lives and how it improves their quality of life, and that should have value, and we should be able to put some dollars to it, within our healthcare system. Okay, so the other thing, I'm going to skip through these slides here and go to the next continuum. Remember I said there was a continuum strategy? And remember that slide where there was no EMG activity? Okay, there was no EMG activity. So I'm very committed to my work in the science and all the translation that happens, and I'm very fortunate to be able to be a part of it. But I'll tell you that my true passion is figuring out what to do with Asia A's. What can we do with Asia A's? This is my passion, especially those Asia A's that have been injured for many, many years. And so this is where we focus our basic science, and it's in a human. I call it human basic science in the lab. And I'm very fortunate to have longtime collaborators, Yuri Yerezmenko, who's from Russia, and also spent some time at UCLA, Reggie Edgerton, who was my postdoc mentor, and now my longtime colleague at UCLA, Joel Burdick at Caltech, and Jonathan Hodes, who's the chair of our department and is the neurosurgeon. And we're all collaborating on this study. And this study is experimental. And this is Claudia Angeli. Here's them again. Claudia Angeli is the one who manages the day-to-day project. And we actually have an advisory board for this project because it involves an epidural stimulation surgical implant. And so we want to get the best advice from around the world. And we're very fortunate to have these people who advise us. And this is the the research team that conducts these studies, which are incredibly, incredibly difficult to do. So I'm so fortunate to have such a fantastic research team. Okay, now, again, I'm not going to go into the detail, but let's go back to the animals. So we've shown that these networks, these interneurons, are in the human spinal cord. So now we're going to go back and we're going to relook at everything we know from the animal literature. And one of the things that we have known from the animal literature is that if you combine training with drugs and with epidural stimulation, rats can regain the ability to step, okay? And so I'm not going to go through the details of this information, but what I want you to know about this is a rat here, and you see the same EMG activity. Without the stimulation and with no load, or with the stimulation with no load, you don't get any activity. You can see that from before. But if you start loading, you start getting that activity. So what's important about this is they're constantly stimulating the spinal cord, and you don't see anything. Okay? Remember that pattern and that pattern with no EMG activity in the human? Keep that in your mind. But if I stimulate and load and give it the right sensory information, you suddenly start getting activity. Okay, the other thing is that with the stimulation on, if you turn the rat around, it can walk front ways, back ways, and sideways. Same stimulation, but what's different? What's different about walking forward and backward? The information, the sensory information coming in is different. So this is a completely transected rat, and the spinal cord, if given stimulation, can interpret that information and walk all those different ways on a treadmill. Okay, so what our team, oops, come on. Okay, what our team, whoop, I'm sorry, I went the wrong way here. Okay. Let's try that. Oh, no, I went there. Sorry, guys. I don't know why this isn't moving forward. All right, so what our team did is we assembled a group of international experts, and we said, look at these results in the rat. We know we have this evidence that the human does have these properties. Are we ready to see if epidural stimulation will work in a human? And when we first did the study, what we were really looking for, we were not looking for improvement. We weren't trying to have people improve. We were just going to put the stimulator in to see experimentally if we could get these results. And so we took people who had zero pattern, and the first person had a C7 injury, Asia B now. This is an Asia B, so had some sensation, but absolutely no motor activity. And what we did is we record from the muscles like you've seen before. We monitored heart function. And what we did is we trained him first for 80 sessions. And then we did all kinds of evaluations. We did a surgery. We put a stimulator over the spinal cord. I'll show you later. And then we did stand training and we did step training. And the idea was this was someone who could the stimulator work like it did in the rat. So this is a person, this is our first person that we stimulated. And what you see down here, here's what his EMG looked like, 0. And we trained him for 80 sessions, actually 170 sessions, actually. And what was at the end of it? 0. And here you can see after 170 sessions, very little activity. Oh, there we go. So this shows you us stepping him. This is not with the stimulator or standing, and you see that we always have to have our hands on him. Every 170 sessions, always have our hands on him for when he's standing or he's stepping. Okay, and this just shows that. So what we did is we put a stimulator in the spinal cord. So these are levels, the lumbosacrospinal cord, the levels of the spinal cord. We did that surgically. And then we mapped this system, and we were able to figure out where to place it correctly. And I won't go into these details, but we did this in the surgery, so we knew where to put it right over those interneurons that we thought were there. And this was going to enable us to see if we could stimulate and see those interneurons. Now, what was very shocking to us is the third day of stimulation, we got this alternating step-like pattern with just the stimulator on, stepping. So this was more than we really expected. But even more surprising is the first time we put this individual up back on the body weight support, we put a specific configuration in, and we started increasing the voltage. And you can see the voltage is flipping here, and this is the data on the left for those of you into. But what you really do, watch the trainers. Do you see they start being able, we go up in the voltage, and they could take their hands off. And the first time we tried to stand him, he was able to stand. Now, this is at a high body weight support. So then we said, well, let's lower the body weight support. And this is what we're doing here, and we're lowering the body weight support. So this is someone 3 years after injury. He was not able to stand. And do you see that trainer scratching his head? He was very surprised and confused about how this could happen. We could get this independent standing. And so it was very, very surprising. Now, then we did, and the muscle contraction is really strong. We trained him for 80 sessions. And just what this shows down here is it's showing that over time, he could stand independently for a longer period of time. Now, do you see what does that look like, that clonus? What we found was he could stand at first for 3 minutes, and then he would break into clonus, and then it would go away. But remember, that stimulator's on all the time. And when the stimulator's on and there's no loading information, the muscles are silent. What the spinal stimulator does is it excites these inner neurons so they can work again. And this just shows, that he's able to stand over ground. I'll show you again. And this is him being able to do this independently. So as he was trained more, he was able to say, okay, I'm ready to stand, let go, I'm going to stand by myself. And as he continued to train, he was able to stand for longer and longer periods of time. Okay. Now, one day, we were doing a long, boring experiment, very expensive experiment, and I was standing looking at the monitor. And remember, this is about locomotion. This is not about voluntary control. Even I knew that you had to have the brain to get voluntary movement. I knew that. I was sure of it. And these two right here, this is Rebecca. She works, and this is our first person. And they're whispering back there, and I'm thinking, oh, don't they know how important this experiment? What are they talking about the movies? What are they talking about? I was getting a little stressed out. And Rob said to me, Susie, take a look at this. And I turned around, and this is what I saw, okay? This is not what I saw, but first what I want to show you is this is him trying to move. Oh, could you put that sound on now? I'd like to have that audio. Is that possible? You put that sound on? Okay, so what I'm doing right now is I'm asking him to push his left ankle down, bring his right leg up. Okay, he's an Asia B. His motor scores are 0. He can't do it. In fact, we had just recently done an Asia, and he still could not move his legs on command. Okay, no activity whatsoever. But, are we good with it? Hopefully we can hear this now. You can hear. When we turn the stimulator on, this is what happens.
Up, left toe down, left leg up, left leg down, left leg up, left leg down, left ankle up, left ankle down, left leg up, left leg down, left toe up, left toe down.
And after I saw that, I wasn't stressed out anymore. So this is a really important lesson for us, and I think something we have to think about as the spinal cord injury community, as researchers, as clinicians, as people who are living with spinal cord injury. We don't know everything. There are things we don't know. And I think that is exciting because we're working furiously to figure this out. And Rob said to me, Susie, how is this happening? And I looked at him and I said, I have absolutely no idea. I have some reading to do this weekend. And so what I will tell you now is that we have repeated these results in 2 more people. So we've implanted 3 people right now. All of them are able to stand with the stimulator on. It's another B and one A. Okay, all of them are able to move like this, and when we practice, it gets better and better. Longer standing, stronger movements, better movements that can be tied to that. So we had to go back and rethink our entire theory. And I'm going to tell you that when we saw this, we thought it was the combination of training. And so when we did our second person, because these are just so many experiments, I don't go to all the experiments. Claudia and I trade off. Either I'm at an experiment or she is. And before we started the epidural stimulation training, they tested this person. So the first person we didn't test before the epidural stimulation because we knew we couldn't move. We knew that was never going to happen. Okay, that's not a good scientist right there. Don't assume. And I learned a lesson. And I'm always preaching to my students. And I fell into that trap. But then I did it again, and I said, well, good luck with that experiment. Oh, it's going to be boring because we know he's not going to be able to move. He hasn't been trained yet. And the first time we tried it with him, he was able to move. Not very well. And I said, okay, okay, I get it now. I'm not going to make any more assumptions. And again, I think that's really exciting. So we have an Asia A and 2 Asia Bs. The first 3 people that we've tried are able to stand and they're able to move their legs. Now, why is this? Why do we think this is? We had to go back to our theory. Because first of all, the spinal cord is smart, and it's a decision maker, and it can understand the information coming in. After a spinal cord injury, though, I think what happens is its excitability goes away, some more than others. And so even though it still could function, it's like there's no gain. It's like it's too, you have to crank it up. And that's what the stimulator does. It cranks it up, and now it can interpret that information. And if we keep it up there, then it can do things that it could do before the injury because it's at that level. And what we find over time is as we go, how much we have to stimulate starts going down. So the spinal cord seems to stay changed. It's plastic. It can change. So we are just beginning to scratch the surface to understand how this is happening. And what I'm going to end with is that's the team. That's my wonderful, fabulous team. But what I want to end with is to tell you that other things are changing. Heart function, breathing, circulation, temperature control, even some bladder control. And we're just starting to understand this. So I think that this is one of the times that when you open up a can of worms, you're really happy. So there's going to be lots more experiments coming. And what we want to do and what we're committed and devoted to do is to try to translate new findings out into the SCI community as quickly as we can. And that's what we want to do is going forward. And I want to say that Chris and Dana Reeve, had they not been so supportive of the SCI community, I would not be standing here today. So I want to take a minute to thank them and to acknowledge how they changed the field because they got money so that we could do these experiments and also obviously let the world know about spinal cord injury so people became more interested in it. So I'd like to end there, and I would be happy to answer anybody's questions. And thank you so much again for inviting me and let me share the story with you. I think there's someone in the middle.
Hi, thank you. It's really unbelievable. Once the implant is in, does it ever come out?
We don't know.
Okay.
So let me tell you, we're just learning every day. We learn something new. The original design of the experiment was that they would keep the stimulator in and that we would take it back out, but it was their choice if they wanted to keep it or take it out. So that was the original experiment, and so far everyone wants to keep it in.
We have some questions on the webcast, okay. And the first is, will there be a home-based version of a system that can trigger the same oscillations?
So that's the goal, right? So this is the goal, and there's lots of challenges to translation, and we're trying to work through them. But that's what we want to do. So one of the things right now to really understand is the technology that we used was an off-the-shelf device for pain. And so it wasn't designed for this, so that's part of what was very surprising. But it's not, and it's not designed for this, so there's no control algorithm. I'm the control algorithm. Claudia's the control algorithm. So we have to decide what the configurations and voltages and everything are, and then we program this kind of limited interface, and then they can use it at home or practice at home. But it's not in a situation now where you say, okay, I want to stand up to do the dishes. The technology's not there. But we did just get a very generous gift from the Helmsley Foundation to help us build another stimulator and move towards that. So there's a lot of work to do before it's going to be practical in something that can help in the home and the community. But there are now sort of these other benefits that I think that they are happy that they have.
We have some more questions on the webcast. And it seems to be an important question. How does one become a subject in your research?
Okay. So what you do is you contact us in Louisville, and if you just go look us up on the web, well, actually, there's a Facebook page. If you search me on Facebook, I can't believe I'm saying this, but if you search me on Facebook, it'll get you there. Or if you just go to Frazier Rehab Institute or University of Louisville and you go through the web, there's a way that you can enter in your information, or there's contact information. But what you do is you just contact us. You tell us that you want to be put in our database, and then and we'll take your information, and then that's how you get to a point where you're going to be initially screened. But I want to caution everybody. We have approval right now to do 2 more from the FDA. Okay, so right now, is not a very likely time that it's not a very likely time. So I don't want you to think if you do that, we're going to be calling you on Monday to be part of the study, and it's a very, very long process. But what we also want to do for you is to tell you what is going on and keep you informed. We have many grants out now so that we can increase the number of people that we can implant from an experimental and health standpoint, and we're working on that, but it's probably going to be some time before we're able to do a higher number of people.
I can keep going, but I can't see if there are other questions.
Okay?
With the implants in, is there an improvement in sensation?
Yes, there is also improvement in sensation. So in these three individuals.
Are you familiar with, on PBS with Alan Alda from MASH?
Uh-huh.
There was a program where they had a stimulator on a woman who, she wore a pack in front of her, and she was at a supermarket, she could turn the pack on, and she was able to stand. Is this anything like that?
Well, it's different, and here's the difference. Those kinds of systems stimulate the muscles directly. Okay, so they're stimulating the muscles directly. We're up here stimulating the spinal cord. So it's different.
Thank you.
Does all of your research, is it restricted to just central nervous system, or is there any inclusion for lower motor neuron injuries?
Yeah, so that's a very good question. So the lower motor neuron injury is more complicated from this perspective. Okay, because where those inner neurons are is where that in the lumbosacral cord. So if you have an injury there, you might have injured some of these interneurons. In addition, with what's called an upper motor neuron injury, which is if your injury is T12 or above, okay, the nerves that come from your spinal cord to the muscle are in that lower part. So what you've done is you've caused a disconnection from the input from the brain, but you still have those motor neurons going to the muscle. So right now, in a lower motor neuron injury, you face 2 additional challenges. One is you have that spinal cord injury, so you're hitting those inner neurons, but you've also probably injured some of the neurons to the muscles. So it's more complicated. So in our research, we don't study individuals with lower motor neuron. But that doesn't necessarily mean as an individual who has lower motor neuron that some of these strategies can't help.
We're not going to make assumptions. We're not going to make assumptions.
Yeah. So, well, and the thing about this, too, is just to expand on your question, when you think about other causes of paralysis like stroke or cerebral palsy, all that occur above T12, okay? This should also, locomotor training itself without the epidural stimulation and in combination, this could also be a strategy for those, because what you're doing is you're targeting those inner neurons in the lumbosacral cord and you're reteaching them to function again. And so just kind of to follow up, expand on your question. Yeah?
My name is Gerard Plant. I'm 37 years post-injury. And I had the good fortune to go to Craig Hospital and then go to Colorado. It's a world-renowned spinal cord rehab. I'm sure you're familiar with it.
Mm-hmm.
So over the past couple of decades, just to name just more recent, they've made several advances in quality of life issues related to people with spinal cord injury, such as helping people get off ventilators.
Yes.
And currently they have some sort of system, I forget what it's called. They just get their newsletter in January and showed some extensive article on getting people to stand and even walk who hadn't in many years. So I'm just wondering, I saw your team of centers that you have listed up there. Mm-hmm. So where's Craig Hospital in all this?
In the Neuro Recovery Network?
Yeah, only because they've been a world-renowned spinal cord rehab center for, over 5 decades, and
right.
They have They had a collaboration here with Boston Medical Center for many years, and then
right.
They have a collaboration with Karolinska Institute in Sweden,
yeah.
which is like the spinal cord rehab in Europe.
Right.
So I'm just very interested in knowing where Craig Hospital is and all this.
Yeah. So there was a process in selecting the centers, and in the future we may be expanding to other centers like Craig. When we started, there was a very specific process, and people needed to apply and come in, and that's how the selection process happened. So. Everything's sort of resource limited, but we're really hoping to expand the NRN to other both centers and community fitness and wellness facilities.
They were never a consideration?
I think it's sort of, it's not that they weren't a consideration, it's just through that process. It wasn't something I think at that time was maybe something that they were looking for. But I think that in the future, you might see some other centers that as part of the Neuro Recovery Network. I mean, when we first started, it was very new and novel and very uncertain. And I think now that we're more established, you might see other centers joining.
With the Neuro Recovery Network in Boston closing, where can people in the Boston area access these kinds of therapies? Yeah,
I know. So that's a very very important and tough question to answer. One of the things that I do want to tell you, though, is I don't have a good answer for you, but I'm going to tell you that one of the things that the Neuro Recovery Network is doing is we try to train as many centers as we can, and one of our focus is to try to make this more available. And so we're going to work very hard on it. I don't have a quick answer for you right now, but I would stay posted on the Christopher and Dana Reeve website, and as we expand out, hopefully it will re-engage this area so that people who do live here have a place to go closer. Do you have any more from the web?
We have more for the webcast. Okay. And one is, how long do these effects last? Are they permanent?
So again, we don't know. This is so new. But what I can tell you is that our first individual is now probably almost 3 years from the original, maybe 2 years from the original implant. And he is still seeing these effects, and they are continuing to improve, if you will. He's able to move more often and have stronger contractions and stand for longer time. So, but this is all new. So, you know, I'll be able to tell you more every year about what's happening from a long-term perspective, and hopefully as we have more people who are implanted, what will happen. So it's all very, very new. So we don't know the answers to a lot of questions. But so far, what the gains have continued, and they have not gone away. Yeah.
I was wondering, what level do you put the implants, and how many implants does it take to actually get any lower movement?
Well, so it took 3. We first try, but where we put it is in the lumbosacrospinal cord, so the very lower part of your spinal cord, and that's where we know from animals that these smart interneurons are. So we're really trying to get to those interneurons and those networks to excite them so that they can re-engage. Now, as we know, not walking, we were thinking about it that it would only be possible to try to help walking, but with standing and voluntary movement. So these are very low part, not where your injury is, not where the injury is. Okay, it's below the injury. The injury for the experiments needs to be above that level, so above T10. So they've all been either high T1, T2, or cervical. So it's not where the injury is. It's right where these interneurons are. Okay? Let's see if I can move over here so I can see you.
Do you speculate if you did functional MRI on the brain of an Asia A and turn on the spinal stimulator, would you see feedback or communication?
Yeah, so, of course, that's a very important question and one we want to answer. So you can't put people in the magnet after they're implanted. So we can't do that experiment, but we are developing an experiment to try to electrically test pathways and try to understand not really the afferent piece, but the efferent piece, and see, so one interpretation of this is a person's Asia A, right, but they're not anatomically complete. I think maybe that's to what you're getting at. And we don't know those answers, but we're working really hard to design new experiments so we can try to understand what's happening. Is there something, there's lots of possibilities that there were latent pathways that now the stimulator is unmasking, if you will. They've always been there. There's always been a connection, but we haven't been able to observe them with our clinical testing. Another possibility is that the stimulator itself is retrogradely stimulating some sprouting maybe around the injury. All these things are very possible. I mean, the other way out there is we assume, and I'm still, now I have learned my lesson. I'm not assuming anything. But I think we all would theorize that the intent is still at the brain. The only other possibility is that there's intent in the spinal cord. It can be driven, right? That would really be shocking. Really turn what we've thought in the past upside down. So I think the more likely is the first two, and probably a combination of those. But we're working hard to try to test them.
And second question, histologically, where are these awesome interneurons? Have they always been there before and you've known their location, or are they? Well,
we've known from animal experiments where they're located, right? And so really this was to demonstrate whether or not they exist in the humans. That's all we were really trying to get out of this first experiment. And then we saw these behavioral changes, so it changed a lot of what we're doing. So we knew from the animal literature where we would expect to find them. But again, it was thought that humans didn't have these properties, that when the brain evolved, it took over all those things that in other species is regulated at the spinal cord. Because of course, there's lots of animals that don't have a cortex that can walk or swim, right? And locomote. So, okay, I think in the middle.
I was wondering if any of the people you experimented with had any experience with Fez bike technology or any kind of muscular development because of that.
Yep. So so the answer is yes. When they entered the study, though, they were no longer. We asked them not to do that because, of course, it's an experiment. And we want to know it's what we're doing. so I'll just tell you a little more. In our community fitness and wellness centers, functional electrical stimulation is one of the things that are offered there. In our rehabilitation, we don't do functional electrical stimulation because we don't know if that might confuse the relearning. And so that's an experiment we're also doing in the lab now with collaborators from Edmonton and Kessler, is to try to see if that kind of stimulation, because this is what you were bringing up before where you directly stimulate the muscles, how does that fit into the spinal cord? Because when you do that, it's different information, sensory information than that's not been known before. So how does that impact that? And we don't know. So, but I think that I think that stimulating your muscles below the injury, if that's the best way you can do it, then I think it's important to do that, right? Because it keeps your muscles strong. And so even if the learning is confusing, these guys did FES before, they stopped, and you have these results. So they're, I think that I would say that it's an important thing to do if that's the best way you can get your muscles contracting below your lesion.
I was just curious about the interneurons just being in the lumbosacral spine, because I know, for example, in pain management, when we think of central sensitization, we think of it at every level.
Yeah.
So was it just...
Well, so there's a lot of scientific debate about that, okay? And so there's a group of scientists who feel very strongly that it's in L1, L2. And so, but there's also some evidence that these, if you would say central pattern generators, exist through the entire axis. But I kind of think about it a different way, is that it's the properties of neurons that allow this to happen. And so, and if you took an interneuron from the brain in the spinal cord and you put them in two dishes and mixed it up, you probably couldn't tell which was which. So it's probably the intrinsic properties of neurons and how they function and how they aggregate and how they form networks that allow this behavior. So when I think about this, I really don't think that it is that there's very discrete place, but there's no good evidence there's great evidence to know that these interneurons exist at this part of the cord. The other evidence is difficult to test and isn't as strong. So, but I think that with this voluntary activity, what if we put a stimulator up in the cervical region, and could we get arm function?
Maybe for stroke you could do upper extremity.
Yeah. So I think that, and again, right, we got to leave everything on the table after what we've just seen, right? So, but that's also on the drawing. We'd like to pursue that. It's a bit complicated because there's no good animal model, So, but I think that's possible. I do, and it's something we want to study.
So, Susie, actually, we are out of time over here.
Oh, okay.
Thank you very much. This was fascinating, and thank you for coming up to do this.
Thank you for having me. Oh, here.
And before Steve speaks, I just want to remind everyone to fill out your survey. If you don't have one, raise your hands. We have some volunteers who will go around the room and fill one out and hand you one, and then hand them in at the end.
So thank you all for coming tonight, and thank you who are participating on the webcast. I'm glad that you were all able to hear this important talk. I think it's very exciting, and I look forward to lots of good things coming out of Dr. Harkema's lab. Tonight, remember, as I was also going to say, to complete your survey. It's important information for us. Also, if you would like a certificate for attending tonight, they're located in the back of the room, and I would just ask that everybody be safe on your way home. So we'll see you in May at the next lecture series. Thank you so much.